just get started. Hello, everyone. My name is Hsiao, a PhD student at Stanford University, working with Professor Caroline Trippel. I'm excited to tell you about our work for design for hardware memory model verification. This is joint work with our collaborators at University of Virginia. Let's consider a concurrent program where two cores share memory at address x and y. Core 0 writes 1 to x and then 1 to y. And core 1 prints conditionally depending on the value it reads for y and x. Depending on the interleaving of threads, we may see different results, such as only will is printed. More importantly, the result may depend also on the memory consistency model or MCM of the hardware on which this program is run. For example, the result of hello only is permitted on ARM machine, but is forbidden on Intel processor, as ARM memory model allows reordering of write operation versus x86 TSO disallows such reordering. That is, memory consistency model restricts the ordering and visibility of shared memory accesses on a multiprocessor, and therefore the outcome of a parallel program. Since microarchitecture must correctly implement MCM specified by their Yasas to correctly execute this parallel program, an important question is how do we verify a specific microarchitecture indeed implements a given ISA level MCM? One could try to construct individual proof for every microarchitecture. Prior work adopts a top-down approach that tries to map a high-level ordering rule such in the instruction level to a set of signals and properties in Verilog. Such approach it lacks scalability and completeness. Verifying an industry design for its MCM implementation takes a whole team of engineers month or more, and typically requires resorted to boundary proof. Not to mention, you need to do so for every generation of your microarchitecture. In our work, we take a different approach and ask if we can synthesize an abstract model of hardware for MCM verification. Specifically, hardware proposes a suite of tools called the check tools that verify hardware MCM implementation. It's taken as an input axiomatic model of MCM implementation of your microarchitecture called Mixedback Model to prove compliance to ISA level MCM. Analysis on the check tool has been demonstrated effective in identifying real bugs in processor, compiler, and MCM specification. And the analysis on Mixedback model is efficient because it abstracts away combinational logic and returns only information about state updates and their ordering behaviors, and which are necessary and sufficient condition for memory consistency model to be correct. However, Mixedback model has been manually written, and Mixedback model basically it means it's not proven upheld by your actual Verilog implementation. Therefore, our prior work of RTO to Mixedback took the first step in synthesizing a proven correct Mixedback model from RTO directly. Unfortunately, there are some limitations to apply RTO to Mixedback to complex processors such as ARM machine, and including limited support for design with certain features. I will go into detail later. So this talk, I will focus on some of these limitations, how we plan to address them. And before I do so, I'll introduce Mixedback model in more details and how RTO to Mixedback works. Specifically, a Mixedback model encodes ordering behavior of design using a set of axioms written in first-order logic DSO. For example, the Mixedback model shown in the middle represents the processor on the left. And it enables an analysis called microarchitectural happens before analysis that model hardware-specific program execution as directed graph called RISC-V graph. Given a litmus test, which is a small program that encodes ordering behavior of your ISA level MCM, such as the one shown on the top. According to the Mixedback model, we can instantiate a RISC-V graph on the right, which represents a specific microarchitectural execution of this litmus test program with this particular outcome running on this particular hardware. Within the graph, row labels are sets of state elements in the core. For example, the IF row level represents pipeline register in instruction batch state on the left. A column of nodes represent instruction execution through the pipeline. Say this highlighted column represents I0 in the original program. Within a column, and those represent hardware events, which corresponds to instruction updating a particular set of state elements. So the directed age indicate happens before relation between events. And it is the Mixedback model decides its nodes and ages. For example, this particular axiom uses add-age construct to describe a set of happens before relation for all the write operation on this particular hardware. One of them saying the store operation always update instruction fetch stage before it updates DX stage, which instantiate the two nodes and ages on the right. Finally, a cycle in the MHB graph indicate an impossible sequencing of an event where one event must have happened before itself, and implies this particular execution is not possible. Therefore, to verify a litmus test always execute correctly on this microarchitecture, the check tool search all microarchitectural execution of this input program on this hardware design, and make sure all the corresponding MHB graph corresponding to illegal outcome are sickly, meaning forbidden outcomes are not observable on this hardware. And Mixedback model are what enable check tools to conduct such a search, since it determines the nodes and ages to construct a MHB graph. Therefore, the correctness proof of the check tool depends on the fidelity of your Mixedback model. As mentioned, it had been manually written, and to extend the guarantee down to the RTO level, RTO to Mixedback is proposed to synthesize this proven Mixedback model. So it leveraged the insights that the static analysis of on the netlist of all control data flow graph of a design can produce an over-approximation of all possible Mixedback axioms to be included. The over-approximation is embedded in SystemVerilog assertion, or SVA, to be evaluated against the original design using JasperGo, a model checker. Based on the evaluation result, which prove or disapprove a properties, RTO to Mixedback select those proven ones to construct a correct by construction Mixedback model. This synthesized axioms are proven ordering rules describing per-instruction execution path or instruction interaction, which specify the blue and red edges respectively on the right. Say one rule specifies store instruction update execution stage in program order, and therefore the red edge on the right. We conduct a case study on multi-V scale that implements sequential consistency. RTO to Mixedback was able to synthesize a model with all property completed, and prove it indeed complies with sequential consistency using check tool. Whereas the prior work of RTO check takes a top-down approach and gave an incomplete proof. The completeness arises from the bottom-up approach we adopt, where properties are generated is localized in the sense that every property refers to a small footprint of our design and generally reference hardware state elements that are connected directly through the combinational logic in the netlist. And while this improves over prior work, we have several, RTO to Mixedback can only handle simple processor due to several limitations. So some of them are related to the feature of input design. One is it has limited support for a design where instruction exhibit multiple execution paths. An example is a design feature in cache where memory operation can have a cache miss versus cache hit path as shown on the right. Previously, RTO to Mixedback cannot synthesize a complete Mixedback axioms capturing both paths because it assumes if an instruction ever updates an state elements, it always updates a previous state element. And some other limitation includes no support of cache coherence or limited assumption on the instruction interaction. We're in the process of resolving them, but due to time limit, I will not go into details, but as a side note, I will talk about it in tomorrow's Oscar workshop and their relevance for hardware security verification. For the remainder of the talk, I'd like to focus on scalability of this property-driven approach. Specifically, this approach relies on the evaluation of SVA properties, as you probably observed. Previously, in our case study, all properties are complete in the case of multi-V scale. Namely, for each property we generate, the model checker can either prove the property always holds for all the possible hardware traces, or disapprove with a counterexample. However, as we scale to larger design, we may see that the model checker produces an incomplete or undetermined result, meaning it doesn't know if it always will be true. It can only say the property is true up to a certain bound, say 10 cycle from the reset. While common techniques such as modularization, abstraction, as verification engineers can use, can address some of these undetermined results. Not all undetermined property can be resolved due to being too complex from complex data dependency. Therefore, for the remainder of the talk, I'll motivate for the case for addressing undetermined outcomes and how we plan to resolve them with design for verification. As a concrete example, consider this processor that features store buffer and implements TSO memory model. We run RTO to Mixedback again on this processor. Different from previous example, there are now axioms whose corresponding SVA properties return undetermined outcome by the model checker. Say the memory has a large amount of fan-in, model checker can really say deterministically for sure that store will always update memory in program order. Therefore, we hand this partial Mixedback. Since we cannot prove them, RTO to Mixedback cannot really include them in the synthesized Mixedback model. And therefore, we have to hand this partial Mixedback to the check tool after discarding the undetermined ordering rules to verify MCM implementation. In the unfortunate case, check tool shows us this partial Mixedback model doesn't represent this processor, now doesn't satisfy TSO memory model. Namely, we can find an MCM violation that say this forbidden litmus test on the left is actually observable on this machine as shown on the right-hand side with the cyclic MHP graph. There are two possibilities. Either your processor design has a real bug, or it's likely due to our Mixedback model being partial by missing some of the ODM rules that are discarded because of undetermined outcomes. We can determine the case by taking a look at the undetermined properties we discarded earlier. That is, say we add back all these undetermined ages and see if we can restore the correctness of, correct the MCM violation. And for this particular litmus test, this indeed make the graph cyclic again and make the MCM correct. Therefore, to restore this MCM compliance, the axioms corresponding to undetermined properties needs a way to be proved. But how can we address them since it's too complex to be proven statically by the model checker? So we propose here to make the use of verifiable monitor that checks for difficult to prove property at runtime. Specifically for an undetermined ordering relation, we will modify the design by adding a small finite state machine that will preserve the ordering between two events by raising a flag or flushing the processor when it detects a ordering violation during the runtime. Together in the pre-silicon phase, we can statically and separately verify this particular small monitor that always correctly monitor the ordering between two events we are interested in, and therefore the undetermined rules can be used to construct a Mixedback model on which the check tool can verify the processor complies with ISA level MCM. Hence, such a design for verification could be a potential solution to the bounded proof we have been stuck with. So now we need a verifiable runtime monitor that has low overhead in area and power. Forward has already proposed a framework that is able to generate correct by construction kind of runtime monitor that checks for a given formula expressed in linear temporal logic. Their case study shows a really good result in area and power. And another potential issue is whether the event we are monitoring are far away from each other, and therefore we need to instantiate the monitor at the highest level of our design. Say, actually, you monitor two events at two cores, and we need a long wire coming out of two cores. And thanks to the design of RTO to Mixedback, the ordering relation it generates are localized, meaning every ordering relation are concerned with state elements of updates that are kind of at most one flip-flop away, and therefore the monitor should be instantiated locally within a module, or a pipeline stage. And therefore, we should not have the case such an issue thanks to the design of RTO to Mixedback and the ordering relation. And however, one obvious catch is how many such monitors should we add to the design? As mentioned, original RTO to Mixedback take a rather brute force generate over approximation, proving all ordering relation between pairs of state elements that it can derive from the netlist. That is, there may be some ordering relation regarding instruction execution not necessarily required to have MCM to be upheld, such as the one highlighted in the red circle that are not necessary to make the graph cyclic again. Therefore, we plan to leverage counterexample guided abstraction refinement to find a minimal set of ordering relations that are required to uphold the MCM. Essentially, we will develop a search procedure to find a minimal set of undetermined ages that are required to achieve MCM compliance, such as a result of, and use such result to use direct insertion of the runtime monitor. So in conclusion, our pilot of RTO to Mixedback is the first one to synthesize a Mixedback model from RTO for efficient memory consistency verification. However, it can only be applied to simple processor, and we have two directions to improve upon. On one hand, we need more support with various features and instruction exhibiting multiple execution behavior. On the other hand, it's the scalability of the property, and as RTO to Mixedback depends on the evaluation of SVA properties. The major issue is undetermined proof outcome, which we propose a verifiable hardware monitor to address such undetermined result at runtime. And in doing so, we will also have an overhead in added this hardware, and so we propose counterexample guided abstraction refinement as a solution to address that. Here ends my talk. Thanks for listening.